All right, so far we talked about like first order circuits. We said like first order circuits are the circuits that only have one storage element. And the way that we could solve for whatever we wanted, whatever we were interested in the circuit, we said we have to write down a differential equation. And that differential equation must be differential equation for voltage across the capacitor or the inductor. Because we knew voltage across the capacitor and current through inductor are the only variables that we were sure are continuous, right? And then we wrote down a differential equation. When we solved the differential equations, we found the initial conditions, found basically the constants, and that was basically the solution, right? We could solve for like whatever else that we wanted from the circuit based off of voltage across the capacitor or current through the inductor. But what we observed was it doesn't matter like what we're trying to solve for. The solution always is exponential as long as the sources that I have in the circuit is constant sources. So I know the solution is always some constant k1 plus some constant k2 times e to the power of minus t over tau, right? Where the tau was our time constant. So it did not really matter like what we were solving for. The solution always looked like an exponential as long as we had like a constant source in the circuit. So what if we started by that solution and worked our way back to find k1, k2, and tau? Then we didn't really have to write the differential equation. We knew what the solution was, k1 plus k2 e to the power of minus t over tau. We found k1, k2, and tau. So we know exactly like what the solution is, right? And we call this method step-by-step method. We briefly talked about it like last lecture. What we're going to be doing today, we're just going to go over it like quickly, just make sure that we know like the steps, and we're going to do a few examples to just make sure we understand it exactly. Okay, so let me quickly remind you what we have. Reminder. Step-by-step method. And again, we're assuming constant sources. And remember that those the constant sources resulted in a constant force function, right? All right, so the first step was assume the solution is xt, which has the exponential form k1 plus k2 e to the power of minus t over tau for all times that are greater than 0, right? The main difference between this method and other methods that we talked about, the differential equation method, is that we're not writing any differential equation. So we don't really have to like write this xt as voltage across the capacitor or current through the inductor. So this xt can be anything in the circuit. It could be voltage across a resistor, it could be current through a resistor, or it even could be current through a capacitor. None of these things are actually continuous. But we still know the solution should look like this. So let me quickly note down. In this case, xt does not need to be voltage across a capacitor or current through an inductor. Okay? So it could be anything. It could be whatever we're interested in, that particular circuit that we're trying to solve. Now we know the solution looks like this. We're going to have to find k1, k2, and tau. Let's just start off by k1. If I look at the limit of this xt, when t goes to infinity, what happens? Basically, this term over here vanishes because e to the power of negative infinity, that goes to 0, right? So all I'm left with is just k1. So if I solve the circuit at time infinity, I can immediately find k1. But keep that in mind. At time infinity, we did not require any continuity condition. At time infinity, we had a circuit. All we needed to know was at time infinity, everything in this circuit is constant. Therefore, we're in a steady state condition. Which meant if I have a capacitor, I had to like replace it by an open circuit. And if I have like an inductor, I have to replace it by a short circuit. And since we do not require any continuity condition, we can immediately compute x evaluated at time infinity. Right? So K1 is easy. So at time t approaching infinity, we know limit of xt when t goes to infinity is indeed K1. So at time t going to infinity, we are in steady state condition, which means if I have a capacitor, I have to replace it by an open circuit, or if I have an inductor, I have to replace it by a short circuit. And then we can compute x at time infinity. Right? We did not need to have any continuity condition. Right? How do we find K2? Well, if I look at my solution, which I know it's K1 plus K2 e to the power minus t over tau, this solution only holds true for times that are greater than 0. Right? So if I evaluate that x at time 0 plus, what do I get? I get K1 plus K2 e to the power of 0, which is 1. So to find K2, if I evaluate x at time 0 plus, that is K1 plus K2. Here's where we have issue. Since x is not necessarily a continuous variable, I do not know if x at time 0 plus is the same as x at time 0 negative. Unless this x is voltage across the capacitor or current through inductor, this x is not continuous. So this does not equal to x at time 0 negative. Again, we do not know if x of t is continuous. Right? So we cannot use this equality there. I don't know if x at time 0 plus is the same as x at time 0 negative. What do we know? What we know is if I have a capacitor or an inductor in the circuit, voltage across the capacitor and current through inductor, they are always continuous variables. I know that. Regardless of x, those variables are continuous. So if I look at my circuit at time 0 negative, I still can compute VC at time 0 negative and IL at time 0 negative. And because of its continuity, what it means that if I actually go a little bit after 0, I'm not going to have a huge jump for voltage across the capacitor or current through the inductor. It's continuous. It means like my function is pretty nice. It's not going to have like a crazy jump if I change it a little bit. Basically going from 0 negative to 0 plus, it's a very tiny change. So for this tiny change, I'm not going to have a huge jump for voltage across the capacitor or current through inductor. So what if I replace my capacitor with a voltage source with value VC at time 0 negative, and my inductor with the current source with value IL at time 0 negative at time 0 plus? What changes? Nothing. Because remember, the value of the voltage across the capacitor would not change by much. And since it's actually like continuous, if I look at it immediately before 0 and immediately after 0, the value of voltage across capacitor remains the same. So is current through inductor. So I can replace my capacitor by a voltage source and replace my inductor by current source. Now I have a circuit at time 0 plus that does not have any capacitor or inductor in it. Now I can simply solve for x at time 0 plus. So to find x at time 0 plus, we're going to have to go through these steps. To find x at time 0 plus, the first step is look at the circuit at time 0 negative and compute VC at time 0 negative or IL at time 0 negative. Since these variables are continuous, we know they're the same as these values at 0 plus. Since VC and IL are continuous, VC at time 0 negative is the same as VC at time 0 positive. IL at time 0 negative is the same as IL at time 0 plus. But here's the thing, at time 0 minus, what's happening in the circuit? Again, we're in a steady state condition because everything in the circuit is constant, right? So to find VC at time 0 negative, I'm still in a steady state condition, which means if I have a capacitor, I have to open it. If I have an inductor, I got to short it out. So at time t equals 0 negative, we're in a steady state condition. Now we're going to invoke the continuity condition, which tells us voltage across the capacitor cannot jump, current through inductor cannot jump either. So I can replace my capacitor with a voltage source or my inductor with a current source. Now we look at the circuit at time t equals 0 plus. We replace a capacitor with a voltage source with value VC 0 negative, which we know it's the same as VC at 0 positive, and an inductor with a current source with value IL 0 negative. Right? And as soon as I do this, I have no capacitor or no inductor in my circuit. I have a resistive circuit. I can solve for x at time 0 plus. Part C, since there is no capacitor or inductor in the circuit, at time t equals 0 plus, we can simply solve for x at time 0 plus, right? And as soon as I know x at time 0 plus, I know k1 and k2. Because we already found k1, I know x at time 0 plus is k1 plus k2. I know k2, right? Only if I can find tau, then I know everything about the solution. But the tau is like very simple. If you recall, we talked about like RC circuits and RL circuits. And we said if you have an RC circuit, the time constant for an RC circuit is RC, and the time constant for an RL circuit is L over R. And we know whatever circuit that we have, as long as it has like one capacitor or one inductor, can be simplified down to an RC circuit or an RL circuit. We only need to look at the capacitor or the inductor as our load and the rest of the circuit as a black box. I'm fine like R-Thevenin for it. Right? So we can simplify it down to either like an RC circuit or an RL circuit, depending on if you have like a capacitor or an inductor. So the tau part is like very simple. So next step is to find time constant tau. We know for an RC circuit, tau is R-Thevenin times C. For an RL circuit, tau is L over R-Thevenin. Now we're done. We know K1, we know K2, we know tau. Therefore, we know X of t. 5, the solution is xt equals K1 plus K2 e to the power of minus t over tau for all times that are greater than 0. Right? So the main idea here is that we're going to have to use the continuity condition at t equals 0, right? And solve for Vc or IL. And since there's not going to be a huge change for these values, we can replace the capacitor by a voltage source at time 0 plus, or the inductor with a current source with value IL at time 0 negative at time 0 plus, and then solve for x at time 0 plus, since we don't really have the continuity condition for x at time 0 plus. Right? That is the whole idea behind it. Okay? Any question about these steps? Is that clear why we're doing these steps? Yes? Yes? So let's do an example and try to apply these steps and see like how it actually works. Let's just say I'm given a circuit that looks like this. So 2 Henry followed by another 6 and a 24 volts source. And I have a switch over here, which I know it'll be open at time 0. Right? And the question is, what is this I naught for time greater than 0? First of all, that arrow on the switch that tells us if it's actually becoming open or closed, right? Since the arrow is actually like going downward, it means at time 0, it's going to be open, right? Obviously, we can solve for this I naught using like differential equation method, right? But could we write a differential equation for I naught? Well, obviously we could, but it's useless. Why? Because if I write a differential equation for I naught is current through the resistor. I don't know if it's continuous or not. As a matter of fact, it is not. We're going to actually see it. And since it's not continuous, it's not going to help me find the initial conditions. So if I wanted to write down the differential equation, I had to write down the differential equation for current through the inductor, because that was our continuous variable. But the good news here is that since we're doing like step-by-step method, we don't really have to write a differential equation. We can just assume the solution, which is I naught, has exponential form. So we want to do this like by step-by-step method. Again, since we're doing step-by-step, we can assume this I naught has this form, K1 plus K2 e to the power of minus t over tau for all times that are greater than 0. Right? We do not really need to have any continuity condition, at the moment. So we're going to assume the solution is this. All we got to do is to find K1, K2, and tau. And as long as I have those three, I'm done. So let's start by K1. Find K1. Remember, to find K1, the solution is still this. So if I look at this circuit at time infinity, which means this portion vanishes, this portion goes to 0, I end up getting this K1. So let's look at the circuit at time infinity. So look at the circuit at time approaching infinity. But what's the circuit look like at time infinity? Well, I know at time infinity is still like greater than 0. What it means is that the switch is open. Right? What happens if the switch is open? What it means is that this portion of the circuit is completely gone. Because this is open. So there's no current flowing through here. So this portion of the circuit is gone, and this is my circuit. Right? So this is my circuit for all times that are greater than 0. Right? And current through this is I naught of t. But this is not exactly like what I'm interested in. What I'm interested in is this circuit at time infinity. What's happening at time infinity? We're in a steady state condition, which means if I have an inductor, I have to replace it by a short circuit. So at time infinity, my circuit becomes this. And this is I naught infinity. What is I naught infinity then? What is it? It's 0. There is no source in the circuit. Right? So I know I naught at time infinity is 0. What does that tell me? It tells me K1 must be 0. Right? This wasn't too bad, right? Now our job is to find K2, right? To be able to find K2, we need to look at I naught at 0 plus. So we need to find K2, which we need to know I naught at 0 plus. Right? But how do we do this? We know I naught is not continuous. So instead, we're going to look at the circuit at time 0 negative and find VC or IL at time 0 negative. So the circuit at time t equals 0 negative, let's just see like what it looks like. What's happening to the circuit at time 0 negative? At time 0 negative, it's before time 0, right? Which means the switch is closed. So I have like the full circuit. But remember, if I have the full circuit over there, everything in this circuit is constant. Which means I'm in a steady state condition. Right? If I'm in a steady state condition, what happens to the inductor? It becomes short circuit. So at time 0 negative, my circuit is this. I have the 6. My inductor becomes short circuit. I have this 6. I have this 24, and the switch is closed. All I have to do is I have to find IL at time 0 negative. Right? Do you agree this is I naught at time 0 negative? Do we even care about this I naught at time 0 negative? We don't, right? Because we don't know if I naught at time 0 negative is the same as I naught at time 0 positive. But just for the sake of conversation, let's just find it over here. Right? What is IL at time 0 negative. What is it? Well, I just need to write a KVL for this loop on the right, right? So if I write a KVL for this loop, I get IL at time 0 negative as 24 divided by 6, which is 4 amps. Right? I have negative 24 plus 6 times IL, 0. Therefore, IL is 24 divided by 6. Right? I know immediately this is IL at time 0 plus. Right? But like I said, for the sake of conversation, what is I naught at time 0 negative? It's 0. Right? I just need to write a KVL here in this loop on the left. Right? So I know I naught at time 0 negative is actually 0. Right? Again, we don't really care about it. I just want you to see if it's continuous or not. Right? Now I know IL, I know current through inductor, is indeed continuous. Right? So if I look at the circuit at time 0 plus, the value of current through inductor cannot change drastically. So I can replace the inductor by a current source with that value. So at time t equals 0 plus, again, I'm going to have to look at the circuit at time 0 plus, which is a little after 0, which means this portion of the circuit is gone. Right? And all I have to do is I have to replace this inductor by current source. So I have 6. I have my inductor replaced by a current source. And the value of this current source is 4, which is IL at time 0 negative. Right? Now I have the circuit. I can find this I naught at time 0 plus. What is I naught at time 0 plus? It's negative 4. Right? So I naught at time 0 plus is negative 4. Do you see what's happening here? I naught at 0 negative is 0. I naught at 0 plus is negative 4. You see the discrepancy? You see it's not actually continuous? So if I wanted to write down a differential equation, I couldn't use that. Right? But the good news is, right now I know I naught at 0 plus. I know that's K1 plus K2. So I naught at time 0 plus is K1 plus K2. We know that's negative 4. We just found K1, and we know that is 0. Right? Therefore, K2 must be negative 4. The unit for I naught is amps, right? So far, we found K1. We found K2. All we got to do is to find tau. Right? So next step is to find tau. Yes. Yes. Do you agree this is my circuit? Do you agree at time 0, the switch opens? If the switch opens, it means there is no current flowing through here. It means this portion of the circuit is gone. Right? And therefore, this is what I have. One thing that's very, very important is that this is the direction of IL at time 0 negative. I assume it's downwards. And therefore, the direction of the current source that I have here is downwards. Right? If I assume this direction is upward, the value would have found was -4, and the value that I should have had over here was a current source going upward with the value -4. Right? Keep that in mind. Yes. What was your question? Okay. So how do we find tau? Again, we have to find tau for all times that are greater than 0. So we're going to look at the circuit at time greater than 0. We're going to think of the inductor as our load and the rest of the circuit as the black box and find our Thevenin. Right? So for time greater than 0, again, my circuit looks like this. This is my load. And I have to find our Thevenin here. What is our Thevenin? What is it? There's only one resistance, it's 6, right? So our Thevenin is 6 ohms. What is tau then? This is an LR circuit. Tau is L over R Thevenin. So this is L over R Thevenin. L is 2. R Thevenin is 6. So it's 1/3. And the unit is second. Right? I have K1. I have K2. I have tau. I know exactly what I through that resistor is. So I know I naught of t is K1 plus K2 e to the power of minus t over tau. We found K1 to be 0, K2 to be -4, so I have -4, e to the power of minus t over tau. Tau is 1/3, so it's going to be -3t for all times greater than 0. Right? And the unit here is amps, because whatever we found was in amps. Right? Any question? Any question? Let's do one more example. Let's do one more example to just make sure it clicks. Example. Let's just say I am given this circuit. It's a 36, 2K, 100 microfarad, a 6K, and let's just say we have a switch that we know it closes at t equal 0. I have a 4K, and I have a 12 volts. And the question is, what is IT for time greater than 0? Obviously, we can write a differential equation for voltage across this capacitor. Remember, we cannot write a differential equation for IT because it's not continuous. If we wanted to solve this using differential equation method, we had to write a differential equation for voltage across the capacitor and then solve for all the constants and then find IT. Right? Good news is, since we're doing step-by-step method, we already know what IT looks like. IT should look like an exponential. So we know IT is some constant K1 plus K2 e to the minus t over tau for all times greater than 0. Right? Now we got to find K1, K2, and tau. For K1, since it satisfies this equation, I know if I look at the circuit at time infinity, that would produce K1. Right? So to find K1, we're going to look at the circuit as time approaches infinity. What happens at time infinity? At time infinity, I know the switch is closed. And I also know I'm in a steady state condition. Therefore, my capacitor becomes an open circuit. Right? So my circuit would look like this. I have 36. I have a 2K. My capacitor becomes open. I have a 6K. My switch is closed. I have a 4K. And I have a 12 volts. Do I even care about voltage across this capacitor at time infinity? No. All we care about is this I at time infinity, right? We're not concerned with this voltage across because we're not solving for voltage across capacitor, right? And we don't have any continuity issue. So all we need to do is to find this I at time infinity. How can we find it? Well, it's very simple, right? I can just write a KVL here, right? So I have 2K times I infinity plus 6K times I infinity equals 36, right? Therefore, I infinity is 36 divided by 8K, which is 9/2 milliamps, right? As soon as I know I infinity, I know exactly what K1 is, right? Because K1 is I infinity. Therefore, K1 is I infinity, it's 9/2, right? I found K1. Let's move on to K2. To be able to know what K2 is, I need to evaluate this I at 0 plus, right? So we need to find K2. Therefore, we need to know I at time 0 plus, which gives us K1 plus K2, right? But we do know I at time 0 plus is not I at time 0 minus, right? There is no continuity there. So what we need to do is to look at the circuit at time 0 negative and find the variables that are continuous, right? What's the circuit look like at time 0 negative? Well, obviously the switch is open, right? What happens to the capacitor? Again, we're in a steady state condition. So it's going to be open. But this time, I am interested in voltage across the capacitor because that is my continuous variable. And I'm trying to find all the continuous functions, right? So my circuit would look like this. I have this 36. I have 2K. This is VC at time 0 negative. I have a 6K. The switch is open. I have a 4K. And I have a 12 volts. Do I even care about this I at time 0 negative? No, because I do know I at time 0 negative is not the same as I at time 0 plus. So I don't even care. I'm not even going to compute it. Well, I am, just because to show it to you, but like, I don't need to compute it, right? So how do we find this VC? Well, let's just write a KVL, right? I can write a KVL over here, right? Let's just call this current I, which I know I is exactly I at time 0 negative, right? Let's just call it I. What do I have? I have 2I plus 6I plus 4I plus 12 minus 36 equals 0, right? Which tells me 12Ki is 24. Therefore, I is 2 milliamps, right? Right? It's just a KVL. Which again, that tells us I at 0 negative is the same as I and it's 2 milliamps, right? Right? Well, still not done yet. You still have to like find VC at time 0 negative. Right? How do I find VC at time 0 negative? Well, I'm just going to write a little like KVL over here. Right? So if I write it, I have 2 times I minus 36 plus VC 0 negative. That must be 0. Right? Therefore, VC 0 negative is 36 minus 2I, which is 4. So it's going to be 32. Right? Therefore, VC at 0 positive is exactly the same as VC at time 0 negative minus 32. Right? Again, I do know voltage across the capacitor is a continuous variable. So if I go from 0 negative to 0 plus, the value of voltage across capacitor would not jump. So I can replace my capacitor with a voltage source with value 32 at time 0 plus. So I'm going to go back to the circuit. I'm going to look at it at time 0 plus. So at time 0 plus. First of all, what does my circuit look like? The switch is closed. This capacitor was replaced by a voltage source with value 32. So if I redraw it, it would look like this. I have this 36. I have this 2K. I have this 6K. This is closed. I have this 4K. And I have this 12. What is the polarity for my capacitor? Remember, I assume this is positive, this is negative. So this should be positive, this should be negative, and the value is 32. Right? So that basically coincides with this one. Right? So how do we find I at time 0 plus? Because that's what we're interested in. Right? How do we find it? I just need to write a KVL here. Right? So if I write a KVL here, I have 6K times I at time 0 plus equals 32. Therefore, I at time 0 plus is 32 divided by 6K, which is 16 over 3 milliamps. Right? That tells immediately to me that K1 plus K2 is 16 over 3. Right? Remember, I at time 0 plus is K1 plus K2. Therefore, I know K1 plus K2 is 16 over 3. Right? We already found K1. K1 is 9 over 2. Therefore, we know K2 is 16 over 3 minus 9 over 2. The common denominator is 6, so it would be 5 over 6. Right? We found K1, found K2. All we need to do is to find tau. How do we find tau? We're going to look at the circuit at time greater than 0, and we're going to find our Thevenin, which is equivalent resistance across that capacitor. So we're going to have to find tau for all times greater than 0. So what does the circuit look like? Well, this is closed, right? So my circuit would look like this. I have this 36. I have 2K. I have 100 microfarad. I have a 6K. I have a 4K. And I have this 12. Right? So I'm going to look at my capacitor as the load, and whatever I have around it would be my black box. So I know how to find R Thevenin for that black box. How do we find R Thevenin? Well, we're going to look at the black box. If there is no dependent source, we're going to zero out the sources, and we're going to find the equivalent resistance. If there is a dependent source in it, what we do is that we're going to look at this load. We're going to find V open circuit across it. We're going to short out the load. We're going to find current through it, which we call I short circuit. And we're going to divide V open circuit by I short circuit, and that's R Thevenin. Right? This circuit is an easy one. If I look at the black box, there's absolutely no dependent source in it. So to find R Thevenin, I have to zero out the sources and find the equivalent resistance. How do I zero out voltage sources? I got to short them out. I got to set the value 0. If a value of voltage source is 0, it means it's a short circuit. So my circuit actually looks like this. So I'm going to short out this 36. I have this 2K. This is where my load is located. I have a 6K. I have this 4K. And I'm going to have to short out this 12. Right? And the idea is that find R equivalent here. Right? Do you agree this 4K is gone? Why? It's in parallel with the wire. Right? So it's gone. So my circuit is only this portion of it. So what is my R equivalent then? What is the relationship between this 6K and 2K? What is it? Parallel. Right? They're sharing the exact same head and tail. Right? So our equivalent is 6K in parallel with 2K, which is 12 divided by 8 kilo ohms. You guys see it? You guys see they're actually in parallel? They share the exact same head and tail. So this is basically the head of 6K, which is the same as head of 2K. This is the tail of this 6K, which is the same as tail of this 2K. So they're in parallel. Right? They're not in series. They're not back to back because we don't know what's going on in the middle here. So whatever current I have through this 2K is not going to entirely flow through this 6K. So they're not in series. Right? Now I have R equivalent. I can find time constant. This is an RC circuit. For an RC circuit, time constant is R Thevenin times C. So time constant, tau, is R Thevenin times C, which is 12 over 8 K times 100 microfarad. Right? 12 over 8K means like 12 over 8 times 10 to the power of 3. I have 100, which means like 10 to the power of 2. I have a micro, which means 10 to the power of minus 6. So I have 10 to the power of 5 times 10 to the power of minus 6. So it's 10 to the power of minus 1. So the whole thing over here is 12 over 8 times 10 to the power of minus 1 second. Right? I found K1. I found K2. I found tau. I know exactly like what the solution is. I know IT is K1 plus K2, e to the power of minus t over tau, for all times greater than 0. What is my unit here? We found everything in terms of like milliamps, right? Everything is in milli. Therefore, this is going to be milliamps. Right? Any question on this? Is that clear how we're approaching these kind of problems? So what we're going to be doing next week, we're going to start talking about second order circuits with constant sources. And we're going to learn how to solve a second order differential equation. We're going to go through like different solutions for a second order differential equation. And then we're going to say, okay, what if our source is not a constant source? What if our source is a sine wave? We said, like, okay, we still can write that differential equation, but it's hard to solve a differential equation with a sine wave. So we're going to come up with like another method, which we call it phasor method. That's basically our plan for the next 2 weeks. All right, I'll see you guys next week.